These are notes for Honors Math 3 on 6.7. These are hyperbolas, and this is the day 1 set of notes for today. So we'll start with the definition of a hyperbola, which is the set of all points in a plane whose distance from two fixed points is a constant difference. The constant difference is 2a, and this is going to be the length of our transverse axis. So we have some different vocabulary here when it comes to hyperbolas than we do with ellipses, where ellipses have a major and minor axis. Hyperbolas have a transverse and conjugate axis. It's important to know that one does not have to be longer than the other. They can be the same length. The conjugate axis can be longer than our transverse axis, which is our vertex to vertex. And so where ellipses, major and minor, means major is longer and minor is shorter, that's not necessarily the case here. So there's a lot of parts to hyperbolas that you'll want these pictures and copying stuff down here. So of course you have your center, and the center to each vertex is still A. But the focus points are inside of the curve, and so they're actually farther away than each vertex is from the center. So center to focus is still C. The focal length C is slightly different than it was with the ellipses. In this case, you'll add A squared and B squared. So keep in mind that with the ellipses, there's a plus sign here in their equations. And with their focal length C, you end up subtracting the values. When it comes to hyperbolas, there's a minus sign in our equations, and we'll want to add. So I tend to remember it that way, just switching them around. You'll notice with the equations, you still have that x minus h squared, y minus k squared. What's different is a squared is always first, b squared is always second because of the way we write our equations. We typically want to lead off with a positive and so follow up with a negative. So you'll see either positive x squared followed by a negative y squared, or positive y squared followed by a negative x squared. And of course, they're both still equal to 1. So depending on which one is positive, that's the one you're looking for here. Which one is positive tells you which direction it opens. So because I have a positive x squared, my hyperbola opens right and left with the x-axis. Over here, when there's a positive y squared, my hyperbola opens up and down just like the y-axis does. All right. Hyperbolas also are constructed first by creating a box. And so that box, and through the corners of the box, we draw asymptotes, and those are our guidelines, and that is how we'll construct our shape. So we'll get into that when we get to our first example. Remember to write down all of this important information over here of identifying the values. Your center is still HK. E is still C over A, but you'll find since C is a longer distance than A, you should end up with a value that is greater than 1. The transverse axis is the distance from vertex to vertex, which is 2A. Since center to vertex is A, so we get a total distance of 2A there. The conjugate axis is what gives us the other dimension for the box we need to construct. And so center to each edge of that box is B, and so that total length is 2B. Okay. And so again, remember that those axes don't have to be one longer than the other. So your transverse axis can be longer. Sometimes the conjugate axis is the longer axis, and sometimes the two have the same length. All right. The equation for the asymptotes is just writing the equation of a line in point-slope form. So you'll see the slope here, m. The point that we use is actually going to be the center, h. Okay. If you like to get y by itself and add k over here on the end, you can do that. I tend to keep it this way because it looks just like the coordinate pair that we're taking here. From our equation. So you just grab whatever you started with here and plug it in. And then your slope, your rise over run, we'll get that from our box, but it's always either A over B or B over A. Okay, and we'll see that when we get to it. So there's a lot of characteristics to identify here besides the center, vertices, focus points, the length of each transverse and conjugate axis, the value of E, and then writing the equations for the asymptotes, which I just went over, and so we should have an easy enough time with that since they are just equations of lines. All right, so our first example is given by this equation here. We want to see, it's already in its nice standard form. We can see that x squared is positive followed by a negative y squared. So this will tell me the direction that my curve is opening. So with x squared being positive, it should open along the x-axis, which is left and right. So just an idea of what my curve will look like at the end. We'll start with identifying the center as -3, +1. And I'm going to graph as I go. Mark the center here. All right, to construct our endpoints, we would do the same thing we do with the ellipses. We look underneath x squared for the value here. So 4 squared is what gives us 16. 4 squared is what gives us 16. And so 4 is the length I want to move left and right on the x-axis. So 4 units, 1, 2, 3, 4 units to the right, and 1, 2, 3, 4 units to the left to mark some endpoints here. Okay, we do the same along the y-axis. So under y squared is 9, which is 3 squared. So we're always looking at what's being squared. So along the y-axis, we want to move 3 units up and 3 units down. And that's from the center. So these 4 points, instead of connecting with our ellipse, we're making a box. That's going to be the start of how we guide our hyperbola. So I want to remind you that since it's opening left and right, the left and right endpoints here, these are the vertices. So this is actually where my hyperbolas will start and open up. But before we do that, let's go ahead and mark down the coordinate pairs there, -7, 1, and 1, 1. And then we'll start drawing our shape by making the box here. So the points at the top and bottom, that's the top and the bottom of the box we want to make. The vertices on the right and left are passing through the left and right sides of the box. And you just want to make it nice and dotted here. Okay. And this is going to be what helps guide our curves, because through the end corners here of our box, we're going to draw the asymptotes. All right. We can write the equations for these asymptotes right now. That'll be a good thing to practice. So we're going to start with that point slope form here, and we're just going to steal from what we already have. So we always want to start with y. So we have y minus 1 is equal to, we're going to write plus and minus and leave room to find the slope here of x plus 3. And again, you can add that 1 over if you prefer to have y all by itself. So the slope of my lines, if I start from my center, right, we're just counting up and over for slope, rise over run. So the distance that we moved up, well, that was the distance that we went from the center to create the top of the box. So center up was 3, and then run is going to be the same as center to the right side of the box. So that's the value that we used for x here. And so we have 3 over 4. Easiest to count from center to a corner of the box, although you could count from one corner to another. You would just have to reduce once you get that value of 6/8 to 3/4. Okay. The length of the transverse and conjugate axes. So the transverse axis, that's vertex to vertex. So here all the way over to here. So we've got 4 and 4, which is 8. The conjugate axis is this other axis here, top to bottom. So 3 up and 3 down is a total length of 6. And to find E, we do need C, so we still need to find our focus points. We need to finish our picture as well. So now that I have all of my guideline curves, we're going to start from each vertex and just follow the asymptotes out. All right, so that is our finished picture. Let's find the focus points. We're going to need the focal length C. So we're going to do the root of a squared plus b squared. So it's just adding the numbers underneath together. So 16 and 9. So we end up with root 25 or 5. And so from our center, we would go right 5 units and left 5 units to find the focus points here. So taking the center, if we start here, to move right and left, you're adjusting the x value. So we're going to take the x value here and we're going to add and subtract 5, right? So plus and minus 5 both ways. So if we start at -3 and add 5, we end up at 2, same y value 1. If we start at -3 and subtract 5, we end up at -8, same y value 1. So now to fill in E, which is C over A, we have 5 divided by A. Now A is always center to vertex. So center to vertex, that would make this A here, and that was our 4 units right and left. So 5 over 4, which is bigger than 1, and that's what we're looking for here. All right. And I think that's all the characteristics, so we should be finished with example number 1. So on example 2, we're going to do the same thing. All I've done here is started with a hyperbola that's opening in a different direction. Now I have y squared followed by a negative x squared. So because we have a positive y squared, this one should be opening up and down along with the y-axis. So our center HK, we want to grab from x first, -1, and then from y, -4. -1, -4, so we'll start there. And then we'll start looking at the square values underneath. So 7 squared makes 49, so that's 7 units along the y-axis. All right, and that is the way it's opening up and down. So these are the vertices for the hyperbola. So we'll label those. We have -1, 3. And -1, -11. So remember, you can also just write it like you can remember to adjust it from the center. You start with your center, and then we're just adding and subtracting onto the y value, plus and minus 7. So adding 7 gets me to 3, subtracting 7 gets me to -11. All right, so to make the left and right side, so how far do I go left and right with the x-axis? 5 units. Just remember to look at the value being squared, so 5 units right and 5 units left. All right, and these will form, we'll take the top, the left side, down to the bottom, and the right side. Through the corners and the center, we'll want to draw the asymptotes. All right, so to write the equation for the asymptotes, we're going to start with our coordinate pair here, and we place y on the left, y plus 4 is equal to plus and minus, and then x plus 1. So that slope, that rise over run, I'm going to count from the center to the corner here. So the distance we went up was how far we went from the center to the vertex. So center to vertex was 7. And then run is the x value. So it's always the value under y and then the value under x. Since slope is always rise over run, it's always the y over the x. So 7 over 5. The length of the transverse axis, so vertex to vertex, so that's 7 up and 7 down, is a total length of 14. The conjugate axis, left and right, so we went 5 left and 5 right for a total length of 10. So in the two examples I've done, the transverse axis has been the longer axis, but just keep in mind it doesn't have to be. So sometimes that shorter axis, you get a wider hyperbola in those cases. And then again, the two axes can be the same length, in which case the box here is a square instead of a rectangle. Let's finish drawing the hyperbola. So starting at the top vertex and opening up and following out with the asymptotes. At the bottom, same thing. And you really want to do your best to show that your curve is getting close to those asymptotes as it follows them out. For the last parts, to find the focal length C, we have a squared plus b squared, so 49 plus 25, which is going to give us the square root of 74. Now, that's not going to simplify. So in order to say that we went up root 74 and down root 74, we're just going to write this as an adjustment of the center. So moving up and down is going to change the y value here. So we're going to keep the x value the same, that's -1. And the y value -4, we add and subtract root 74. And that gets us to the focus points there. So E, being C over A, is root 74 divided by A, which is always center to vertex. Remember, center to the vertex was the distance that we went up and down. And so that was the value under Y, which is 7. So root 74 over 7. So that's example number 2. In the last example, we're going to use the given information here and write the equation for the hyperbola. So you can sketch as you go, since that can be very helpful. We're going to start with vertices 0, 6 and 0, -6. All right, so if these are my vertices that are in line up and down from one another, I've got a few things real quick here. Right in the middle is my center, so it's the origin. And I can also see that it must be opening up and down. So I can start by writing most of my equation with the center plugged in. So it's going to start with a positive y squared, right? And it would be y minus 0 squared over something minus x minus 0 squared over something is equal to 1. So these values here, so the value that goes under y would just be the square of how far we went up and down. So up or down, that's your a value, 6, right? So 6 squared is 36. And now we're just left with finding this value over here. So the last thing they gave me is the equation for the asymptotes. And what I can take from here, I can see that they've plugged in the center, y minus 0, x minus 0. But in front of x is my slope, 1. So because I have a slope of 1, this should be the value of rise over run. So to make that box in here, my rise was center to vertex, which is 6. So in order to get a slope of 1, the run value must also be 6, or the x value that creates the box must also be 6. And so 6 divided by 6 will make 1. And so this distance is also 6 for x, and 6 squared is 36. And you'll see this is what happens when our box is a square and the axes have the same length. So although I have the same coefficient, which typically hints at a circle, I know it's a hyperbola because one of my square variables is negative while the other one is positive. So that is what makes it a hyperbola. And that is the end for the objective 7 notes.